Hello.
Hello. How you doing?
Good, how are you?
Pretty good. Okay, we'll go ahead and get started. Can the people on Zoom hear me and see the screen okay?
Yes.
Thank you. So what we're going to do today is I'm going to review the answers to exam 2. And I just want to remind everyone that the answer key is also posted on Canvas if you want to take a look at it more closely. And then if you have any questions during the review of the answers, just let me know and I'll try and answer it. Then the other thing that we'll do is we'll start on chapter 15, which is the equilibrium chapter. And we'll do part of chapter 15 today, and then we'll finish it up on Tuesday of next week. And then next week on Thursday, so a week from today, we'll have a quiz on chapter 15. And that'll be the last class before spring break. Okay. So the first question, number 1, a solution with a concentration higher than the solubility allows. And the answer to that is it's a supersaturated solution. Then number 2, at elevated temperatures, dinitrogen pentoxide decomposes to nitrogen dioxide and oxygen. And then you're given the chemical equation for that. Then you're told when the rate of formation of NO2 is 5.5 times 10 to the minus 4th molar per second, what's the rate of decomposition of N2O5? The key here was using that stoichiometry in the equation to see that 4 moles of NO2 are formed from 2 moles of N2O5. So to understand that rate of decomposition of N2O5, you needed to take that ratio into account. And so what you would do is you would take the rate of formation of NO2 and divide it by 2 and get a value of 2.8 times 10 to the minus 4. Number 3. Pressure has an appreciable effect on the solubility of, the answer is gases and liquids. Number 4, in general, as temperatures go up, reaction rates, they go up, and it doesn't matter whether it's exothermic or endothermic. Remember, we talked about temperature effects by it speeds things up, kind of makes the molecules move around more. So you increase that chance of a collision occurring. So it doesn't matter if the reaction's endo or exo, it's just you increase the odds of the collision. Number 5, we're told that a solution is prepared by dissolving 25 grams of sodium chloride in 500 grams of water. And then we're asked, what's the molality of the sodium chloride in the solution? So the key here was you needed to remember that molality is moles of solute divided by kilograms of solvent. So to get moles of solute, you needed to calculate the molecular weight of sodium chloride, and that's 58.453. And then use that to convert the 25 grams to moles. And then the amount of water was given in grams, and it needed to be expressed as kilograms. So you needed to convert that 500 grams of water to kilograms. And if you did all that correctly, you would get a value of 0.855 molal. Number 6 is similar, except now we're calculating molarity. And so molarity, remember, is moles of solute per liters of solution. And so we're told that we have some urea, 11.8 grams of urea, and it's in 35 mils of water. And then it's noted that assume that the volume of the solution doesn't change when you dissolve the urea. So you didn't have to do any correction for that 11 gram addition is what that meant. So then it was a case of changing the 11 grams of urea into moles. You were given the molecular weight, so that's the 60 value. So dividing 11 by 60 gives you moles of urea. The volume was in milliliters, 35 mils. So you needed to change that into liters. So converting that into liters in the denominator. And if you did that correctly, you'd get 5.2 molar. Number 7, George is making spaghetti for dinner. He places 4.01 kilograms of water in a pan and brings it to a boil. Before adding the pasta, he added 58 grams of table salt, which is sodium chloride. Add that to the water and then brings it again to the boil. You were asked to calculate what the temperature of that resultant salt water was. And you were told assume 100% ionization of sodium chloride. So in other words, all the sodium chloride breaks into sodium plus ions and Cl minus ions. So a couple things on this. One is, just off the bat, hopefully you saw this as an example of colligative properties. So boiling point elevation was one of the colligative properties. So right off the bat, if you look at the choices for answers, you should have known that it was either 100.26 or 100.13, because boiling point elevation, water boils at 100, so it's not going to be 100, and it's not going to be below 100. It's going to be one of the two above. So then it's just a matter of figuring out, is it 100.26 or 100.13? Remember, we have a formula, delta TB equals I times KB times molality, to tell us what that difference is with the colligative properties. And so then it was a matter of remembering what those variables were and getting things in the right units. So molality, of course, is moles per kilogram of solvent. So we needed to convert our 58 grams of sodium chloride into moles, and we do that by using the molecular weight. And then we need, our water was already in kilograms, so we were good there. So the molal term would be 0.99 moles divided by 4.01 kilogram. We're given, excuse me, we're given the constant 0.52 and so we have that value, we can plug that in, that's good to go. When we were told that the sodium chloride dissolves 100%, then that tells us that the I value, that Van 't Hoff value, is going to be 2, because you have 2 pieces or 2 particles, however you want to think of it, a sodium and a chloride for each of those sodium chloride molecules. So that I value becomes 2, and so now you can do your calculation and find that delta TB is 0.26 degrees C, and then add that to 100 to get 100.26. Number 8, calculate the mole fraction of phosphoric acid, H3PO4, in a 38.5% by mass aqueous solution. So what that tells us is we have phosphoric acid and we have water there. Those are the only 2 things. When it's this weight percent, we always assume for the calculation purpose to use 100 gram total. So that means if we have 100 gram total, we can subtract the 38.5 mass of H3PO4 from 100 to tell us that that means there's 61.5 grams of water. So now we know the grams of water, we know the grams of phosphoric acid. And so since it's a mole fraction we want, it'll be moles of phosphoric acid divided by total moles. So we need to convert both of those into moles. So we need to calculate the molecular weight of phosphoric acid. That comes out to be 98. Molecular weight of water is 18. So in the numerator, we convert that 38.5 grams of phosphoric acid into moles. In the denominator, we have that moles expression for the phosphoric acid, and then 65.1 grams of water divided by 18 to get moles of water. So now we have moles of phosphoric acid divided by moles of phosphoric acid plus moles of water. We go ahead and do all that math, and we get 0.103 as the mole fraction. The next one, emulsifying agents typically have a hydrophobic and a hydrophilic end. So remember, hydrophobic means it doesn't like water, hydrophilic means it likes water. And when we talked about emulsifying agents, we said one of the things they were good for is to take, in a solution, take polar and non-polar molecules, which normally don't want to mix, and serve as kind of a bridge between them. So emulsifying agents usually have a polar end and a non-polar end. And so thus they have a hydrophobic end and a hydrophilic end. So that one was true. Number 10, calculate the concentration in ppm of a solution which is prepared by dissolving 0.024 grams of acetic acid with water to a total weight of 250.6 grams. So whether you're looking for weight percent or ppm or ppb, it's a similar approach. You want to have grams of solute divided by the total grams, and then you're going to multiply it just by a factor depending upon which of those you want. If it's weight percent, it's times 100. If it's ppm, it's times 10 to the 6th. If it's ppb, it's 10 to the 9th. So in this case, we had our 0.024 grams of the acetic acid. Divide that by the 250.6 grams for the total weight. And then we multiply it by 10 to the 6th to give us the ppm value. So remember, that's the whole purpose of the ppm, so you don't have to write all these exponents. Same thing with ppb or percent or any of these things when we express it that way. So I think some people are still getting a little confused on this one. So make sure it's clear in your head that if you do that 10 to the 6th on the calculation, now it's ppm. It's not 9.6 times 10 to the 6th ppm. Okay, so number 11. In number 11, we're told that we have a solution that was prepared by adding 40 grams of lactose to 110 grams of water at 55 degrees C. And then we want to know what the partial pressure of water is above this solution. Some of the other information we're given is the vapor pressure of pure water at this temperature is 118 torr, and the molecular weight of lactose is 342.3. So the key here is remembering that to calculate that pressure, we need the mole fraction of water divided by the pressure, vapor pressure of the pure water at that temperature. When we were given the vapor pressure of the pure water at that temperature, that's the 118 torr. So really what we needed to calculate was the mole fraction of the water. So mole fraction of the water would be the moles of water divided by the total number of moles. So we need to go and calculate the moles of water and then the moles of the lactose. So 40 grams of lactose, we use our 342.3 molecular weight to convert that into 0.117 moles of lactose. The 110 grams of water that were added, we use our molecular weight of 18 for water to convert that into 6.11 moles of water. So now we know the moles of lactose and we know the moles of water. And so we can have 6.11 which is the moles of water divided by 6.111 plus 0.117 moles of water plus moles of lactose. Then we get a mole fraction of 0.98. We go back there and plug that into our formula, and it's 0.918 times 118 gives us that pressure of the water, partial pressure of the water is 115.84. Okay, the next one, number 12. We're told the reaction 2NO2 going to 2NO plus O2 follows second order kinetics. So the key to that is that since we know what order the kinetics are, we know which of those different formulas we talked about that you would use to do the calculation. And we're told that the NO2 concentration drops from 0.01 molar to 0.00650 molar in 100 seconds. And we want to calculate the rate constant. So since it's a second order kinetics reaction, we know we want to use the formula where we have 1 over NO2 concentration equals at some time equals 1 over NO2 concentration at the initial time and plus the constant times the time. So we go ahead and define our K1, or rather our concentration 1 and concentration 2. We go ahead and define the time, and we fill those things in. So 1 over 0.00650 equals 1 over 0.0100 plus the constant times 100 seconds. And then we go ahead and do that math, and we get a value of 0.54 as our constant. Number 13. Reaction is found to be zero order in A. So if you increase the concentration or factor of A by 3, what will happen to the reaction? Well, nothing. Because the key there was remembering that for a zero order reaction, it's not dependent on the concentration of any of the reactants. Okay, 14, the rate constant of a first order process. So once again, knowing the order of the reaction, knowing the order tells us which of those different formulas we want to use. We're told that it's a first order reaction, has a half-life of 3.50 minutes. And we want to know what that is told. Half-life, we want to know what that constant is. So for first order, we know that the half-life equals 0.693 times K. This is the one where the half-life, since it's first order, is not dependent upon any concentration. The only kind of tricky thing was the half-life was given in minutes, 3.5 minutes, and the constant has units of seconds to the -1. So that half-life time needed to be converted into seconds. And so 3.5 minutes is equal to 210 seconds. And so you plug that 210 in, you have your point equals 0.693 divided by K, and then solve by K to get 3.30 times 10 to the -3 inverse seconds. Okay, 15. One difference between first and second order reactions is that the answer is the half-life of the first order reaction does not depend on the initial concentration. The half-life of the second order reaction does depend on this initial concentration. Number 16, for this decomposition reaction, we're told it from A going to B, we're told it's a first order reaction. So then what would be the rate law for it? And the answer is rate equals K times the concentration of A. So since it's first order, no exponents on that concentration or anything like that. 17. What's the magnitude of K for a first order reaction at 75 degrees C if the activation energy is 95.1 kilojoules per mole and the rate constant is 1.35 times 10 to the seconds to the minus 1 at 25 degrees C. So one of the key things here is knowing that it's a first order reaction. So that, and then we can set up our equation, and that's this natural log K1 divided by K2 equals activation energy over R, and then 1 over T2 minus 1 over T1. So the key here is making sure you match up the T1 with the K1 and the T2 with the K2, and also remembering that in terms of units, the temperature's got to be switched into Kelvin from degrees C. So we'll go ahead and change our temperatures into Kelvin. So 25 is 298 Kelvin, 75 is 348 Kelvin. So now we can plug in the T2 and T1 values. So we have 1 over 348 minus 1 over 298. Our gas constant is 8.314. Now, one other thing we have to be aware of is the activation energy is expressed in kilojoules per mole. Because of the gas unit constants units being in joules, that has to be converted into joules. So instead of 95.1, it's 95.1 times 10 to the third. And then finally, our K1 value we were given is 1.35 times 10 to the second, so 135. So then that leaves us to solve for K2. And this is where, you know, a lot of buttons pressing on your calculator. You got to make sure you keep all that straight. The other thing was, this is what we talked about in class. You're going to get to the point of where you have e to the something, in this case, minus 5.15. So hopefully you would practice using your calculator to be able to work with those natural logs and anti-natural logs, and we're comfortable doing that. You know, on problems like this, you know, you got to set them up correctly in the correct units, but then also almost as important is making sure you can keep your calculations straight. And so if you're able to do all that stuff, you would have got an answer of 3.35 times 10 to the fourth. Number 18, in the energy profile of a reaction, the species that exists at the maximum on the curve is called, well, the maximum of the curve is the activation energy, but the species that exists there is the activated complex. So we're looking for activated complex as the answer. 19, colligative properties of solutions include all of the following except, well, they're all colligative properties except reaction rates increasing with increasing temperature. So while that's a true statement, it's not due to colligative properties. Number 20, of the following, which will lower the activation energy for a reaction, and activation energy is lowered by adding a catalyst. Okay, 21, we're told that the overall reaction A plus B to C, that the rate is equal to K times A squared. And so you're asked, which of the following things will not increase the rate of the reaction? Well, the answer is B. And so even though B shows up as a reactant, it's not in the rate equation. So since it's not in the rate equation, that concentration doesn't really matter. Okay, 22. what type of catalyst is used in car catalytic converters, and that's a heterogeneous catalyst. 23, which of the following is most soluble in hexane? So hexane C6H14, hexane's an alkane, a long nonpolar molecule. So we want to know which is the most soluble. So we think back to the like dissolves like. And so we want the compound below that is the most nonpolar, because that'll be the most similar to the hexane. So the one with the most CH2 groups is the one that we want. So it's, let's see, there's 1, 2, there's 5 of them on there, so that's butanol. And so butanol is the answer because that's the most nonpolar of those choices. The hydroxide side it has polarity to it, the other side doesn't. Okay, then 24. The rate of a reaction depends on, well, it's all of these: collision frequency, collision energy, and also collision orientation. So remember, we talked about how the reaction rate is dependent upon the number of collisions. You got to have a collision to take place. So the more collisions, the better. Then it's got to be oriented the correct way. And then also the energy's got to be correct. So we need all those. So the answer was all the choices. And then finally, the last question. This is another one where you got to use your natural log keys and your calculator. So we're told the initial concentration of a reactant in a first order reaction. So once again, knowing the order is helpful to know what formula to use. We're told the initial concentration of the reactant is 0.27 molar, has a rate constant of 0.75 inverse seconds, and then wants to know what's the concentration of the reactant after 0.75 seconds. So we have the natural log of the concentration at whatever time it is we're interested in, divided by that initial concentration, equals minus the constant times the time. So that concentration at some time, in this case, 0.75 seconds, that's what we're trying to find. So that's the unknown. That's divided by 0.27. We want the natural log of all that. And that's equal to minus 0.75 for the constant and 0.75 for the time in seconds. So if you go ahead and do that math, you get to where it's a natural log of that A sub t divided by 0.27 equals minus 0.5625. To be able to solve for AT, we take the antilog of each side. And so then that gets us to where we have the e to the minus 0.5625. So once again, using your calculator to do that calculation, if you do all that correctly, you get 0.15 molar. Any questions about anything on the exam? Okay, so obviously you'll see some of this stuff again on the final, so don't forget it between now and then. And in general, I think people did pretty well on the test, so congratulations on that. That was nice to see. And then we're going to move on to chapter 15 now, in the equilibrium. Let me pull this up. Okay, so the class earlier today I asked, and I guess you guys have not covered this in lab yet. So I wasn't certain if you had or not so far. So what are we talking about when we talk about equilibrium? So we're going to talk about it with respect to chemistry reactions, chemistry processes. But equilibrium is a term that you use just in your everyday life. And it really means the same thing in this chemistry application as it does in just everyday life. So, if you said, oh, I lost my equilibrium and fell down, what would you be saying? You'd be saying I lost my balance, right? And that's when it kind of got out of whack, or however you want to think of it. It's the same with chemistry reactions, is that not all of them, but some of them have where they want to have a certain balance to them. And that's what we're talking about in equilibrium. And so these two pictures you see at the top, I particularly like the one on the left. The one on the right's fine too, but the one on the left I really like, because if we see what that plot is, we see on the x-axis we have time, and on the y-axis we have concentration, okay? And what we're seeing there is, in this particular example, we start with no NO2, okay, so that's the kind of reddish line that you see going up. And we start with some concentration of N2O4. And what we see with time is the N2O4 concentration is decreasing, and the NO2 concentration is increasing. So obviously this reaction is N2O4 converting to NO2. And so at some point here, and it's indicated by the dotted dashed line rather going vertical, that the concentrations don't change anymore. We see the NO2 is a straight line along the top, the N2O4 is a straight line about midway through the graph, but they're the same. That tells us that we've reached equilibrium. That's where that reaction wants to be. It wants to be with that ratio of NO2 to N2O4. The plot on the right is doing a similar thing, but the y-axis is plotting the rate. And so you see there, the NO2, that rate equation, we see that rate value increasing because we start out with nothing, so there's no rate. The N2O4 decreasing, and then we reach the equilibrium. But the one on the left, like I said, I prefer that presentation. And one thing I want to tell you, so when we say something is at equilibrium, we're not saying that the reaction has stopped. Okay, I want to be clear on that. So it just means that the processes, the reaction going forward and the reaction going in reverse are just happening at the same rate, so the concentrations don't change. But it doesn't mean nothing's happening, okay? We call this dynamic equilibrium. And if you think that word dynamic, just in general, it means something's going on. And that's why I'm saying it doesn't make a certain amount of product and then just stay like that. You do have things going back and forth. So the concentrations don't change, but there is this going back and forth to maintain those concentrations. Okay, the way we designate this in chemistry is if we take a look at this reaction, this N2O4 going to NO2, we see in between those two compounds, we have an arrow going to the right and an arrow going to the left. So if you see an equation written with that double arrow like that, that means it's an equilibrium reaction. If it just went one way, then that would tell us it's not an equilibrium reaction. So we don't always pay attention to those arrows, to be honest with you, but this just shows why you should. Because it does tell you something about that reaction, about if it's a lot of decomposition reactions aren't equilibrium reactions. They just decompose and that's it. Not always, but sometimes. And so this is an example of why you want to have, if it is an equilibrium reaction, you want to make sure you put the double arrows in there so that whoever's looking at it knows that's the case. Okay, let's talk a little bit about rates. So here we have that same reaction written, N2O4 going to 2 moles of NO2, and we write that rate law, okay? Then, I remember, how would we have figured out that rate law? We had done experiments, right? And then for the reverse reaction, we go the other way. We have a rate law there. So we've got two rate laws. Since we're in equilibrium, we know that the rate going one way has got to equal the rate going the other way, right? That's the definition of equilibrium. Everything is settled out. So we can set those equal to each other. Then what we can do is, so we set those two equal to each other. We kind of rearrange it. We have the concentration of NO2 squared divided by concentration of N2O4 equal that forward rate constant, reverse rate constant. And so now we're going to combine those two rate constants and define it as another constant, the equilibrium constant. And so then we get equilibrium constant, this KEQ, you'll see it written some other ways too, but equilibrium rate constant equals that ratio that we have there. Okay, let's talk a little bit more about equilibrium rate constants. So here's another example of a chemical reaction. This Haber process is used in industry a lot to make ammonia. So you take nitrogen N2 plus 3 moles of hydrogen H2, and you get 2 moles of NH3, 2 moles of the ammonia. And so because of the double arrows, we know that it's an equilibrium reaction. When you want to express the equilibrium constant, you simply take the products, the concentration of the products, in this case NH3, and divide it by the concentration of the reactants. So product, NH3 divided by reactants, N2 times H2. Now you notice the NH3 has an exponent of 2, the H2 has an exponent of 3. That comes from our balanced chemical equation. So the coefficients on the balanced chemical equation are the exponents in our equilibrium expression. Okay, so we'll talk about this a couple more times because this is important. We need to remember this. But let's talk a little bit about it also visually to kind of see what's going on. So over here on the left, we have, once again, time on the x-axis, concentration on the y-axis. And we see in our reaction, remember, N2 plus H2 going to NH3. So when we start out, we don't have any NH3. We have some amounts of N2 and H2. And as the reaction proceeds, our reactants, H2 and N2, decrease. And our NH3, our product, that concentration increases. And at some point, once again, that's this dotted vertical line, everything levels out and the concentrations remain constant. And that's our equilibrium point. The interesting thing about it is, because it is equilibrium, well, that's kind of looking at it like we normally would, reactants going to products. The same thing happens going the other way. And that's what we see here in the second plot. In this case, we don't have any H2 or N2, but we have some ammonia. And we see that with time, that ammonia will decrease and the H2 and the N2 will increase until once again we arrive at that equilibrium thing. And that's the kind of neat thing about equilibrium, is it goes both ways, right? And that's what you got to remember in terms of this. So just to repeat what I kind of told you a little bit before. So if we think of that equilibrium constant and how we calculate it, if we just look at it like a generic A plus B equals D plus E reaction, if we want to write that equilibrium expression, it's the product of the products divided by the product of the reactants. And so using this example, concentration of D times concentration of E, those are the products, divided by concentration of A, divided by concentration of B, and those exponents that are with each of those, the lowercase a, b, d, e, come from our balanced equation, okay? So depending upon what the coefficients are in the balanced equation, that tells us to what power each of those concentrations need to be in order to calculate our equilibrium constant. So this idea here, products over reactants, then using the coefficients from the balanced chemical equation to be able to know what the exponents are, you have to know this, okay? You have to remember this. The other thing I want to just point out is usually we're talking about concentrations, but sometimes we do talk about pressure, and that's what the equation down below is. But what you'll see is it's essentially the same thing, except you're talking pressure instead of molarity. But it's products over reactants, and then the exponent is based on that stoichiometry. So products over reactants, exponents based on stoichiometry. There's a little bit of information here, but really all it's trying to communicate is that you can compare the equilibrium based on concentration to the pressure by using the ideal gas law. Remember, ideal gas law is PV equals nRT. You can go and kind of rearrange that a little bit. And what you're after, though, is this last equation, this Kp equals Kc times RT to the delta N. And so that's the relationship between the equilibrium constant for pressure versus equilibrium constant for concentration. And R is that ideal gas law constant. T is temperature in Kelvin. Delta N, you see defined down here at the bottom, is moles of the gaseous product minus the moles of the reactant. So this relationship just allows us to see how that ideal gas constant, the equilibrium constant for pressure calculation versus concentration calculation would relate. So when we think of the value of K, if K is a really big number, what would that tell us? Okay. So if K was real big, let's just go back here for a second. We said that the equilibrium constant in this formula in the middle says that it's really what it's saying is concentration of products over concentration of reactants. So if that K value is a big number, do we have more products or more reactants? And more products, because for that K number to be big, the numerator's got to be a lot bigger than the denominator. And then vice versa. If the K value is little, then the denominator needs to be big. So it means we have more reactants than products. So, whoops. So this is kind of spelling that out, but if we really thought about it, we would know that. So if K is a lot bigger than 1, then you form equilibrium likes to have a lot of products. If K is a lot less than 1, then equilibrium likes to have a lot of reactants. And the phrase you made here is this phrase with in the little rectangular box looking thing. Like equilibrium, K greater than 1, equilibrium lies to the right. K less than 1, equilibrium lies to the left. And so remember, left would be more reactants, right? Would be more products. So that's the reason for that kind of little saying that you'll hear people say sometimes. If we know what the equilibrium constant is for a reaction, then the constant for the reverse reactions, in other words, to go the other way, is just 1 over that. It's the reciprocal of that. And that makes sense because we said, in this example, N2O4 going to 2 moles of NO2, if we wrote that rate equation, or that equilibrium expression, it'd be NO2 squared divided by N2O4. And that would be that equilibrium constant. If we wrote the reaction the other way, we would flip that concentration relationship. So if we flip that, then we got to flip the rate constant as well, or the equilibrium constant as well. If you have, remember for the last exam, we talked a little bit about reaction mechanisms. That a lot of times you have steps in reactions. So if you do have that case where you have steps, in this case, we have 2 NOBr going to 2 NO plus Br, and then we have Br2 plus Cl2 going to 2 BrCl. And then we have our overall reaction down at the bottom. If we want to know the rate constant, I keep saying rate constant, equilibrium constant for the whole thing here, we could, and we knew the individual equilibrium constants, we would just simply multiply those individual equilibrium constants together to get what the overall one is. So we've used the terms homogeneous and heterogeneous in the past to describe things. It's no different in this. If it's a homogeneous equilibrium that's going on, that just means all the reactants and all the products are in the same phase. So they're all liquids or they're all gases is the most common examples. Heterogeneous equilibria, that's when you have something, either a reactant or a product that's in a different phase. Probably the most common one on that is you have a solid that's involved in the reaction or a solid that's one of the reaction products. An important thing to remember is that when we're writing out these equilibrium expressions, if we have a pure substance, that concentration is defined as 1. Well, what's a pure substance? A pure substance would be a pure solid or a pure liquid. And here's an example of how that impacts it. So in this case, we have calcium carbonate, which is a solid, going to form calcium oxide, a solid, and then CO2, a gas. So this is an example of a heterogeneous equilibrium, because we've got solids and gases. But when we write that equilibrium expression, remember we said we would have products over reactants. So the products, we have calcium oxide, CaO, and we have CO2, and then in reactants, we have CaCO3. But the only one that shows up in our equilibrium equation is this CO2. And that's because the 2 calcium molecules, those are both in the solid form. So by definition, they're 1. So since it's 1, it doesn't show up in the equilibrium expression. Okay, so up until now, what we've been talking about, we've been talking kind of about equilibrium in general, talking about how, when we talk about chemical equilibrium, we're talking about reactions that go forward and backwards, and they go until they reach a state of where they're happy, think of it that way. And so you have a certain amount of products that are going to be present, a certain amount of reactants that are going to be present. The reaction's still going back and forth, but those concentrations aren't changing. So everything we've talked about so far has been kind of conceptually. Well, at some point, as you probably figured out, we're going to want to use this information that we have in a more quantitative way. We're going to want to be able to do some calculations to understand how the reactions are proceeding, have we reached equilibrium or not, because, and then what is going to happen in terms of how long is it going to take, what are the concentrations, stuff like that. So all of that stuff we talked about before is leading up to what we're going to talk about now. And this slide here, if you're going to spend some time on a slide, spend some time looking at this slide. Because what we're going to go through on this slide is kind of the thought process I would hope you would use to do some of these calculations we're going to discuss. Doesn't mean you have to do it, but I'll tell you, if you can force yourself to kind of to think this way, it'll make life a lot easier. And so let's go through this and see what we're talking about. So if we're trying to understand what some of these equilibrium concentrations are, and by understand, I mean do calculations, the first thing you want to do is you want to set up this table. And I'll show you kind of an example of the table in a little bit. And in that table, what you want to put in is any information that you know. So do you know any of the initial concentrations? If you do, you can plug those into the table. Do you know any equilibrium concentrations? Are you given any of that information? Once again, if you do, you can plug that into the table. You start to set this up. And then you're going to have blanks on the table, and your goal will be to fill in all those blanks. And if you do that, you'll be able to do the calculations appropriately. The next thing you will look at is, do you have anything where the initial and the equilibrium concentration is known? If you know what the initial concentration was, and then you know what the equilibrium concentration is, well, then you can calculate what the change was, right? And that change is useful information. So you want to plug that in if you can do anything there. The next thing is, do you have a balanced chemical equation? So either you were provided one or you were able to figure one out. So make sure your equation is balanced. Why is that important? That's important because that tells us what the relationship is between the products and their reactants in terms of how many moles of the different molecules are interacting. And so that information is going to be useful. You can then use initial concentrations, and if you're able to calculate any changes that occurred based on having any information you had about initial and equilibrium concentrations, and then the stoichiometry of the balanced equation, you can use that to find changes that occurred in the other ones that you weren't given change information on. And then finally, you can calculate the equilibrium constant using all of those equilibrium concentrations that you determined by going through this kind of thought process. So I'll say it again, this is an important slide. You know, we go through a bunch of slides. Not all the slides are created equal. Some are more key to understanding stuff than others. This is a really good one, I think. I like this slide. So let's work through an example to show you how to use this slide that we just went over. And so in this example, we said we have a closed system, and initially it has 1 times 10 to the minus 3rd molar H2. There's 2 times 10 to the minus 3 molar I2. It's at 448 degrees C. It's allowed to reach equilibrium. And down here at the bottom, we have our chemical equation. H2 plus I2 gives us 2 moles of HI. So in that first sentence, we got initial concentrations of our 2 reactants. Down at the bottom, we have a chemical equation. So we already got a few things that we said we were interested in. Now let's look at the second sentence. Analysis of the equilibrium mixture shows that the concentration of HI is 1.87 times 10 to the minus 3 molar. Great, so now we have an equilibrium concentration. Remember we talked about what do we like to have? We'd like to have some initial concentrations. We'd love to have an equilibrium concentration. We'd love to have the reaction equation. So we're in pretty good shape now. So now we want to, our end game is to calculate that equilibrium constant for this reaction. And so let's fill in our table. So we'll call this what do we know table. So if we set this up where we have the concentrations of our reactants and products. And then we say we're going to have one row, that's the initial concentrations, and have a second row that expresses the changes that are undergoing, and a third row that says, what's the concentration at equilibrium? So if we go in and fill in that information that we got in the problem to start with, we know that initially we have 1 times 10 to the minus 3 hydrogen, molar hydrogen. We have 2 times 10 to the minus 3 molar I2. And we knew at the start we don't have any HI, right? We just dumped the H2 and the H2 and the I2 together. Nothing, we haven't done anything initially. So that we can express as 0. We were told the HI concentration is 1.87 times 10 to the minus 3 molar at equilibrium. To get to that equilibrium, what change had to take place there? Well, if we're at 0 and now at 1.87, that means the change for HI had to be plus 1.87, right? What would be the change for H2 and I2? Let's just go back to the formula again. We said if we form 2 moles of HI, we use up 1 mole of I2 and 1 mole of H2, right? We said our change here for HI is 1.87. So that must be twice as much as each of these, the H2 and the I2, right? Because our stoichiometry tells us that 2 moles of this HI get formed from 1 mole of each of those reactants. So if this 2.87 times 10 to the minus 3 represents 2 moles of stuff, then 1 mole of stuff would be half that, right? So let's go ahead and there's our plus. The thing I'll show is if something's forming, we say it's a plus. And then here's our amount of H2 and I2 that was used up to form that. So this 9.35 times 10 to the minus 4 is simply the 1.87 times 10 to the minus 3 divided by 2. So now we know what the changes were, okay? So if I started at 1 times 10 to the minus 3, and I used up 9.35 times 10 to the minus 4, and I'm talking about the H2 column there, how much would I have at equilibrium? What would be how would I figure that out? Any ideas? Well, I can simply just subtract this, right? If it's 1 times 10 to the minus 3, and I use up this 9.35 times 10 to the minus 4, I subtract those, and that, whatever that number is, I can see what that is, I don't know that off the top of my head. 6.5 times 10 to the minus 3, or the 10 to the minus 5, that's my equilibrium concentration for the H2. I do the same thing here on the I2. I subtract this 9.35 times 10 to the minus 4 from 2 times 10 to the minus 3, and I get 1.065 times 10 to the minus 3. So now in my table here, I've got everything I need, right? And so what I can do next is, here's my equilibrium expression. Products over reactants raised to whatever power the coefficients have. So I have HI squared divided by H2 times I2. I plug in those equilibrium numbers I just calculated, and now I get an answer of 51. So just to repeat, we go back to this slide. And remember, we talked about setting up this table. We talked about setting up a table where we have initial and equilibrium concentrations. Then we talked about going through here and seeing what other information we have and start filling in other places that we can. The equation, any concentrations at equilibrium that were given, figuring out changes, and basically going through the thought process that's on this slide to fill in this table. We start here, after we go through the process, we wind up with this. And then next thing we know, we can fill in our equilibrium expression and find that equilibrium constant. So I guarantee you, you're gonna have to do stuff like this on the quiz and exam. So take a look at this example, take a look at the homework, get comfortable doing this type of thing. But the real thing is going back to this slide here, I'm gonna put it up yet again. Whoops. Thinking about this in this manner of how to approach the problem. And like I said, it's kind of a pain in the neck to use this table, at least I think so. And every time I tell myself I'm not going to use it anymore, I'm just going to do this stuff in my head. But I'll tell you, from a bookkeeping and keeping things straight perspective, this is really a good thing to do. So if you can get in that habit, that's a good thing. Any questions on this example or this approach? Okay. There's a similar to that rate, to that equilibrium constant, there's a similar thing that you can calculate called the reaction quotient, and that's Q. It's the same calculation. It's products over reactants. The exponents on those concentrations come from the stoichiometry of the reaction. It's the same thing. It's just a term that's used to give you a feel for how to calculate where things stand at any particular concentration. So basically, it's like at some point in time, where do I stand? Am I close to equilibrium or not? Do I need to form more product? Do I need to have more reactant? Things like that. But that is essentially the same. Here's a more visual showing of that to give you a feel for what this means. If we're at equilibrium, Q equals K, all right? So if we're at equilibrium, Q would equal K. And that's what we're striving to get at. That's what the reaction wants to get to. If Q is less than K, what does that mean? Well, if the number is smaller, once again, for one of these constants to be smaller, the denominator's got to be bigger. The denominator's bigger means we have too many reactants. And so sure enough, we see here in this picture on the right-hand side, if Q is less than K, the reactants are lacking. And so the forward reaction proceeds. Forward reaction proceeding just means you want to form more products. And we think in terms of our ratio that numerator's got to get bigger. Numerator gets bigger by making more products. Once again, if Q and K are equal, that's equilibrium. And then finally, if Q is a lot bigger than K, that means the reactant part is too small, that's the denominator. The numerator, the products, is too big. So that reaction is going to want to go back towards the reactants. So like I said, the Q calculation is exactly the same calculation and setup as for the equilibrium constant. The Q is just doing a calculation using the concentration that you have at that particular time. And what that's useful for is to give you a feel to know if the reaction needs to go forward or go backwards. So in other words, form more products or form more reactants as it tries to get to that equilibrium status. Okay, so if you know the equilibrium constant, you can find out what the equilibrium concentrations are from the initial concentrations and any changes that occur, and knowing what the reaction stoichiometry, so there is that balanced chemical reaction is. You set up a table similar to what we just went through and fill in initial and change and all that. The one big difference is that row, remember we had the row with change and we had numbers. In this case, since you don't know what that is, you use the variable X. And depending on how you use that x, that's based on the stoichiometry of the equation. So we have an example here we're going to go through. At this point, I don't have enough time to get through it in class, so I would prefer to wait until Tuesday to do this. But before we leave, I want to just ask you to do something between now and then. So you may or may not remember this from long ago, but there's something called the quadratic equation. Okay? I guarantee all of you have done this at some point in your life. I also guarantee that you've probably forgotten it. Okay? So the quadratic equation, if you have the textbook, it's explained in Appendix A3, so you can look it up there. But this slide also has what you need to know on it too, if you don't have the book handy. And so what I would ask you to do is to just go and take a look at the quadratic equation, because that's what we're going to need to use to solve these next problems. That's why I say I don't want to go start this example now and get all involved in this and then stop halfway through. But take a look at this quadratic equation. It goes back to this ax squared plus bx plus c equals 0. You take those factors, plug it into this minus b plus or minus square root of b squared minus 4ac, square root of that whole thing, which, you know, if that doesn't give you flashbacks, nothing will. But take a look at this so that you get comfortable solving math like you see down at the bottom here. That's what you're going to lead to. And remember, quadratic equation, which I always love, it gives you two answers, and then you got to pick the answer you want. We'll talk about how you kind of pick those answers too. It's kind of odd, I think, but this is what we'll be using for this next part that we talk about. So we'll go through this in more detail next week on Tuesday. But like I said, take a look at this slide, or if you have your textbook handy, Appendix A3 kind of shows it to you as well. Okay? So we're going to end there for today unless anyone has any questions. All right, thank you. See you on Tuesday.
More flashbacks.
I promised myself I would leave math in last semester.